Hello everyone, welcome back to Chem 400. This is now lecture 4, so we're going to talk about stoichiometry and talk a little bit more about how to set up these problems and do more examples, because we kind of went over mole calculations and using more mass. But now we need to apply that to actual chemical reactions that we will do. So I'm going to take this time to kind of walk us through that, and I may post a video doing more examples. So if students need like a more tutorial-like way of going through these problems, I can do that as well, because I know there will be probably quite a few students who cannot make my office hours, and they prefer to review these things at home with kind of my guidance. So I'm happy to do that. Okay, so stoichiometry, it can be confusing. A lot of people who are not chemistry majors, or like people who didn't major in chemistry, like some of my friends and family, they always tell me they very much disliked stoichiometry. So it was not a very popular topic, and it's one of the most fundamental for understanding and actually practicing chemistry. So we're going to go over this for today. Okay, so think about recipes in cooking, right? You add some of this reagent A, ingredient A, ingredient B, and to get the right ratio, right, to give you the desired product. So if you don't add enough eggs, you don't add enough mix, you don't add enough milk, you're not going to get the pancakes you want. So it's kind of like cooking. If we just think about it in terms of like mixing the right ingredients in the right ratios to get our desired product. Okay, so all right, say our recipe called for 1 cup mix, 3/4 cup of milk, and 1 egg to get 8 pancakes. Okay, so in this situation we could use a fraction because it's cooking, right? So if we have 2 dozen pancakes, right, are needed for a family breakfast, we can increase the amounts proportionally by using this kind of equation here, or recipe, to get the amount of pancakes we want. So say we want 24, right? So we take 24, and we know that for every 8 pancakes we need 1 egg. So we're going to set this up using dimensional analysis. So we know that if we want eggs in the end, we're going to divide by the number of pancakes and multiply by how many eggs it requires. So our ratio is 1 egg over 8 pancakes, and we get 3 eggs. So 24 divided by 8 equals 3. Okay, so that's how we think about stoichiometry. And just imagine, this recipe is just another way of saying, oh, it's like a chemical reaction, right? We put in this reagent versus this reagent, and we get out a product, just like cooking. But unlike chemistry, cooking, we make something, delicious to eat. As for chemistry, we make something, and it could be a food product or part of a food product. Usually pure chemicals are not directly edible. Food are usually a mix of a variety of different materials, chemical compounds, flavoring agents, etc. Pretty much different kinds of like foods and stuff like that. Okay, so now let's take a step back and actually apply it to an actual chemical reaction. So say we're going to predict the amount of oxygen we have to breathe to digest 10 grams of sugar. Okay, so Now, if you start out with this, you might think, oh, we could just use 10 grams of sugar and then just figure out, oh, we've got 10 grams of sugar. We probably need 6 grams of oxygen. Unfortunately, that's not how this works. So in chemical equations, we need to convert grams to mole because 10 grams of sugar is not actually equal to 10 grams of oxygen or 6 grams of oxygen. So we need to convert to the mole scale. So usually when we have grams, we convert to mole. And the chemical equation, it tells us the ratios of each, reactant in terms of moles or moles of substance. It doesn't refer to grams. So in the chemical equation, we cannot simply translate it to grams. Like, oh, 1 gram of glucose or sugar is equal to 6 grams of oxygen. We can't do that. So you see in this equation here, right, this equation here, it's going to be on the mole scale. All right. So how many moles of glucose molecules does 10 grams of this compound contain? So first, we need to know the relationship between grams per mole of a substance, and that is the molecular weight. And on the gram/mole scale, that's called the molar mass. So molecular weight would refer to a single atom or molecule, but usually in chemistry we talk about not just the single atom or molecule, but a bunch of them, a whole lot of them, and usually we refer to that as the mole. So that's our unit of carrying out these chemical reactions by measuring out a mole of something, which we can translate to grams. Okay, step 1. So let's go to step 1. The first step is to convert grams of sugar to moles of sugar. So we know we have 10 grams of sugar, but we need to calculate the molar mass. So if we carry out these calculations, we get 6 carbon atoms times 12.01. That's about 72.06 gram per mole. Okay, hydrogen, going to be 12 times 12.096 grams per mole. And then lastly, oxygen is going to be 6 times 16 or 96 grams per mole. Okay. So for these sig figs, we're going to put out to 2 decimal places because we're adding these values together. So 180.16 grams per mole. So we get 180.16 grams per mole. Okay. So the unit factors is another name for those ratios in dimensional analysis that we use. So now we have a ratio between grams of glucose and moles of glucose. So now we can use that ratio to interconvert between moles and grams. So our factors are 180.16 grams per mole. And then we have also 1 mole is 180.16 grams for glucose. Okay, so these moles and grams are referring to glucose or sugar. Okay, so now let's set up the calculation using our train track method or the dimensional analysis method. So I like to set up these boxes these series of fractions, because they help us get to the right unit we need at the end. So find out what you have. Usually what's on the left is what you have, 10 grams of glucose. But now we want to convert to moles. So we know 1 mole of sugar is, so 1 mole, let's say C6H12O6. Okay, we know that's 180 grams. 0.16 grams. C6H12O6. So that would cancel out the grams. So that will cancel out there. And then what we're left with is moles. See the moles on. See the moles now is going to be the new unit associated with our value. So we essentially have converted everything to moles of sugar. So 0.05551 mole C6H12O6. Okay, so now we can say we have produced this amount of moles of glucose. Or sorry, haven't produced, but we have this amount. Okay, so that is the answer there. Okay, so now let's move on to the next step. Now we look at the balance equation for the reaction. We see for every sugar molecule, so for every one glucose molecule, we have 6 oxygen molecules here, or 6 moles. So our original question was, predict the amount of oxygen we have to breathe to digest this amount of glucose. So now we have all the information we need, the moles of glucose. Now we can write 2 more factors here. So this is what we call the mole ratio, that tells us how much sugar do we need to react with oxygen. So that information, those numbers or ratios, is what we get from the chemical reaction. So it's important that we balance the chemical reaction and that we see the mole ratio and that we can establish the mole ratios. So there's 2 of them here. So 6 moles O2 will react with every 1 mole of glucose. And if we're going from moles of glucose and we want oxygen, this is the ratio we want to use. If instead we started with oxygen and we want to figure out how much glucose we would need to digest, we would do 1 mole C6H12O6 per 6 moles of oxygen. Like that. Okay. Now let's fill out this table here. We have the moles of glucose. Okay. So let's just quickly go back to this calculation here. So see here how we have 4 sig figs in both the starting 10 grams. So here's 4 sig figs. Here's 4 sig figs in our molar mass calculation here. So our final answer should have 4 sig figs. So 4 sig figs in the answer. So we don't want to report every digit, okay? But if you know, since we're using this calculation further, you can keep a few extra digits if you like. I'm not too worried as long as you keep the appropriate number of sig figs in your intermediate answer. You'll be fine. Okay, so we have 0.05551 moles of glucose. So the ratio we want to use is where we cancel out the moles of glucose. So we're going to use 6 moles oxygen, and 6 moles of oxygen is what we want. We want to find the moles of oxygen, so we're going to put the fraction like this. And we multiply through, we get 0.3331 mole oxygen. And there we go. So that's how you would set up a stoichiometry, typical stoichiometry problem. You're given a known amount of the first reagent. or one reactant, and then you're determined to figure out how much of the other reactant you need to react with all of that amount of the first reactant. Okay, and in this case, it's oxygen. We're determining how many moles of oxygen do we need. Okay. So now we have the moles of oxygen, but now we want to figure out we want to know exactly how much oxygen we need. So we want to know how much grams we need. Okay. So now we take that value from before, 0.3331 mole of oxygen, and we have 1 mole of O2. Okay, so the molar mass of oxygen is 16 times 2, right? So that's going to be 32 grams. So we can write up to the side here. O2, so we could say the molar mass. So the molar mass of O2 equals 16.00 times 2 equals 32.00 grams. So you would want to have this, your periodic table handy when doing these problems, so you know how to calculate the molar mass. So you don't have to memorize molar masses. It'll be your responsibility to use the periodic table to figure that out. Okay? So let's be honest. I've been studying chemistry for a long time, and I do not memorize molar masses. I do memorize some compounds, molar masses, because I use them all the time. But usually, like new compounds, I don't memorize. With molar masses, you don't have to memorize molar masses. So if us the experts don't memorize them, you don't have to either. So we'll always provide you with the tools on how to calculate the molar mass. Okay? Grams, oxygen. So there we have it. So that's how we do a typical stoichiometry problem. So let's now sum everything up and fill out this little paragraph here. We need to breathe 10.66 grams of oxygen to digest 10 grams of the glucose that we carry through the bloodstream as our source of energy to fuel our bodies. So if we didn't have hot oxygen, there's no way we could digest this energy, making both oxygen and glucose an essential part of our lives. Okay. So here's a summary of how to do stoichiometry problems. So here is here are some of the steps you should always consider. So when doing problems, you want to consider these steps. Number 1, find the starting material or product of the reaction for which you know the mass and the formula. So we'll usually give you the balanced chemical equation unless we ask you to write it. You may be responsible for that, for translating a word sentence of a chemical reaction into a balanced chemical equation where you have to write the symbols and balance the equation. Okay, so you'll convert the mass to moles. Usually it's given in mass and not moles, but sometimes we'll give you moles. If it's given in moles, you do one less step where you don't convert from grams to moles. Okay. So then we use the balanced chemical equation to figure out the mole ratio between one reactant to another reactant, or from a product to a product, or from a reactant to another product. So we'll use that to determine how much moles of a certain chemical species that we need or that we're trying to find out. Okay? And then we use the molecular weight or the molar mass of the component that we have solved for to convert it to grams. So usually we'll ask for in grams, or we can ask for in moles. It doesn't matter. But after all those steps, you'll be done. So let's do some more examples where we put that into practice. Okay, so how many moles of H2 are required to completely react with 2 moles of carbon monoxide. Okay, so let's end the video here, and we'll pick up on this one in the next video. Okay, see you then.